this lesson we study transmission lines, but now in the frequency domain, so that what we see in terms of voltage and currents are now phasors, which means that they are no longer a function of time, because they represent sinusoidal function of time at generic frequency, angular frequency omega, but they can be a function of space, so that propagation and therefore voltage along the line, as we studied in the time domain, is a wave is actually a complex function of position. So what is the rationale that we want to discuss in the frequency domain? What is the equivalent why we introduce this new element, the transmission line? The finite delay of propagation corresponds to the time domain analysis, but in the frequency domain, what is important, since we know that waves are associated to a wavelength, what is important is the length of the connection between two elements in a circuit in terms of wavelength. So that if the length is much less than the wavelength, let's say 1/100, we can say that this connection is negligible as a general, and if it is not the case, we must take into account the finite length that connects the source, in this case, to a load. So that what we studied in the time domain corresponds to something in this frequency domain that is strictly related. Therefore, the waves that we characterize as arbitrary function of space and time are now function of space. Therefore, we have a voltage, which is a function of space that represents a wave that propagates the positive direction or in the negative direction, and an associated current that represents the current wave. So also in this case, we have in the frequency domain a voltage, which is a function of frequency, a phasor, a complex phasor, and the current that also represents a complex phasor, and the associated fields, which are complex vector phasors, in which the dependency on time is of sinusoidal type. But the relationship between fields and voltage are exactly the same as those that we saw in the time domain. So we have also in this case, as you see, Faraday's law written in the frequency domain, in which now the electric field and the magnetic induction are functions of space, but not functions of time, because they are complex phasors. And we can anyway write Faraday's law applied to this circuit to obtain something very similar to what we found in the time domain. So we have the difference between the two phasors of the voltage that can be written as the derivative, total derivative of the voltage with respect to z times dz must equal minus j omega, which is the operator of minus time derivative for sinusoidal function of time, times the flux per unit length times the length dz of this differential element of transmission line. So that what we find is exactly very, very strictly related to the equivalent equation that we found in the time domain. And specifically, the derivative of the voltage with respect to space, z, the direction of propagation, must equal minus j omega L, the inductance per unit length, times I, which V and I are functions of space but not of time. Similarly, Ampere-Maxwell's law is applied in the same way as we did in the time domain to find that the difference between the two currents that we have at the beginning and at the end of the line must equal minus j omega times q, the charge per unit length, times dz, the length and the infinitesimal length of transmission line. This left-hand term can be written in terms of the derivative of the I with respect to z, and the right-hand term can be written in terms of the capacitance per unit length and the voltage. So that the second equation of the transmission lines is the z derivative of I, the complex phasor representing the current, equals minus j omega c, the capacitance per unit length, times the phasor of the voltage. Also in this case, we can carry out a second derivative operation to both terms and substitute the corresponding expression, so that once we derive twice with respect to z the voltage, what we obtain once we substitute in place of the derivative of I with respect to z its expression as a function of v, what we obtain is a second order equation in v alone, or a second order equation in I alone. these are the equivalent of the wave equation that we saw in the time domain. Are actually wave equations, which is called Helmholtz equations, in the frequency domain. So if we indicate with beta the quantity omega square root of LC, and with V 1 over the square root of LC, which is a speed at which the wave travels, we can obtain the general expression of the waves as a function of Z, in which the generic V function of Z can be written as the value of the phasor for Z equals 0, V naught plus, of the progressive wave, the wave that travels in the positive Z direction, times the wave function exponential minus j beta Z, plus a phasor V naught minus, which represents the value at Z equals 0 on the negative wave, times the wave function in the negative Z direction, which is exponential j beta Z. Similarly, we write a very similar expression for I, and I, we already know that is strictly related to V by the concept of characteristic impedance, so that I can be written as a function of V. As you see, there is a unique coefficient for a single wave, let's say the wave that travels in the positive Z direction. There's a unique coefficient, for instance, V naught plus, that represents the wave, because the two, voltage and currents, are linked by this same coefficient. We have also a very simple and very effective equivalent circuit that represents these quantities. Let's rewrite the two transmission line equations in the frequency domain, in which we have dV over dz, which equals minus j omega L times I, and di over dz, which equals minus j omega C times V. Of course, if we build this circuit in which this element is an inductor whose value is L dz, and this element is a capacitor whose value is C dz, this circuit is capable to represent these two equations that corresponds to a infinitesimal length of transmission line of length dz. Because, as you see, the difference between these two currents with a sign, with a minus sign, is this di. So that di over dz corresponds to the current that flows in this capacitor, and it is linked to the voltage on the capacitor. We are writing actually this same equation. And also, the dV, which is the difference in voltage between V at Z plus dZ minus V dZ, is linked to the current flowing through this inductor. So this circuit is capable to represent in equivalent form these two equations. We'll keep this in mind because it will be very useful also in the study of lines with losses, in which we will introduce further elements into this circuit. So typical transmission lines have parameters that can be computed very easily. Let's see two examples. One is the coaxial transmission line, that is the line that all of us should know because they are used to connect, for instance, the TV to the antenna. This coaxial line is in which there is a material, two concentric, as you see, metallic conductor of some length with some dielectrics inside that supports the inner conductor. The inner radius is A, the outer radius is B, and the expression for characteristic impedance of this coaxial line is shown here, in which there is this eta r, which is the relative impedance, the square root of mu r over epsilon r, that normally is 1 over the square root of epsilon r, because materials are normally non-magnetic. And we have also the expression of the propagation constant is this line that it also depends on the mu r and epsilon r, the relative parameters of the material. Another line is the bifilar line, which is shown here, which there are two wires on the same radius A, placed at a distance d between the centers. Also in this case, we have a closed form expression for the characteristic impedance that is shown here, and for the propagation constant beta that is shown here. The speed of light, speed of the wave that propagates in the transmission line, in the case of homogeneous material in which there is no change of the material, so as you see, like in these two cases, there is no change of the material. In these cases, the speed of the voltage and current waves is the same as the speed of light in the material, and in vacuum, this takes the value 3 times 10 to the power 8 meter per second.